Let's start again. We assume a prior over the distribution parameters theta. So which is p of theta. We assume a likelihood p of d given theta, and then we use the Bayes rule to obtain the posterior p of theta given d, which we cannot compute for a lot of problems. Because the denominator term is intractable. Right? So what did we do in order to solve this problem? If we cannot compute p of d, we cannot use the Bayes rule to obtain the posterior. What do we do? Sorry? Yeah. One such method is to use the Laplace approximation. The formulation is given on the screen. What we are saying is that we can approximate the posterior with a Gaussian, which is parameterized by some psi, where psi is mu and the covariance matrix, and where mu is the mode of the posterior theta map, and the covariance matrix is the negative inverse Hessian of the log joint evaluated at theta map. Right. So we have seen it thus far. What were some limitations with the Laplace approximation?
The constraint of positive semi-definite covariance matrix also.
So what Utkarsh is saying is that we can sometimes face some computational numerical issues because you're computing the Hessian, and sometimes the matrices that you're trying to compute or invert, they're not positive semi-definite. You'll have such issues, but keep them aside. Yes.
Multimodal distribution.
If the posterior is multimodal, you will fix your approximate posterior to one of the mode at whichever the optimization is placed. Any other point?
Hessian computation is
computationally expensive. Like you have to create n cross n, where n is the number of parameters, especially for large problems like neural networks, where the number of parameters can be even in millions. The next approach which we saw was Markov chain Monte Carlo. Here we generate the samples from the posterior distribution. Right? So we typically make a proposal distribution using methods like HMC or Metropolis Hastings, and we typically assume a burn-in period, after which we assume that we have reached stationarity, and after that we draw the samples. We plug those samples directly in the computation of predictive posterior. Right? So that is mainly our goal, to compute the predictive posterior. In Laplace approximation, we first compute the posterior or the approximation to the posterior, and then we can either sample from the posterior, from the approximate posterior, or in certain forms we can directly use certain integrations, closed form solutions, in order to get the predictive posterior. For MCMC, we get the samples, we can plug them in to calculate the predictive posterior. Variational inference will pose the problem of posterior inference as an optimization problem. So typically we like to solve optimization problems in ML. We find them easier, we have convenient frameworks for them. So what we're saying is that we will again approximate the posterior the true posterior p of theta given d with some distribution q of theta, which is parameterized by some psi. Right? For a normal distribution, the psi is mu and covariance matrix. Right? But here we are not restricted by just using the normal distribution. We can use any distribution as our posterior, as our approximate posterior distribution. One, that is the difference. Second, in the Laplace approximation, if you notice, we have fixed the mu value, right, to a certain theta map, and then we are saying that let's calculate the covariance matrix via a certain formulation. But in variational inference, we typically don't assume anything to be fixed. We compute both. So if Q were here indeed a normal distribution, we would compute both, we would try to optimize over both mu and sigma, or the covariance matrix. But as I mentioned, this Q could be a student distribution, it could be a mixture of Gaussians, it could be anything you want. The only thing is you'll have to be able to parameterize it, so that then you can pose an optimization problem, and then you can find out the optimum. Now we also, because we have an optimization problem, we also need an objective. The objective here is the KL divergence between Q and Q of theta and P of theta given d. Right? How many of us have studied KL divergence earlier? Not a lot. Again, it seems the second years have taken some course and they've studied their second and third years, but not the fourth year. So maybe there was some difference in the background in the maths courses. Okay, in which context have you studied the KL divergence? Yes, sir.
I did not study it as a part of course.
Okay. Anyone who studied it as a part of any course? Okay. Okay. An optimization for machine learning course, you would have studied it. Okay. So the KL divergence will be a little new for some of you. We'll first look at some maths, the mathematical formula, and then we'll go back and understand what it does. I'll not go into all of the details and how it is related to information theory. That we'll cover in some other course. So typically you want to measure the dissimilarity between two distributions, right? How similar or dissimilar two distributions are. So if you notice, I'm talking about dissimilarity, not the distance. The notion of distance for probability distributions is not defined, but dissimilarity we can define. So this is the formula KL between given Q and P, right? So the order here is important. It's not a distance metric where the order might not have mattered, but Q and P, if you notice, is the integral of Q theta or the variable of concern, Q theta logarithmic of Q over P theta d theta. And we can also write this in terms of expectations. We can write this quantity as the expected value of log of Q theta by P theta, where theta is distributed as Q. Right, so these two can be considered the equivalent definitions. Enough maths. Now let's go to some code and see. Okay, perhaps the server is down. Okay, you can see that I've created a normal distribution with mean 1 and scale 4. And I have also created another function which can create another Q distribution, which is also a normal distribution given a location and a scale. So I'll generate a few Q distributions. Okay. Now which of Q1 or Q2 do you think is closer to P? Q2, which is shown in green. Why do you say that?
Mean is at the correct place and it's much more flattened compared to Q1. Q1 is much more steep and while the P is quite broad.
Okay, good. So Utkarsh says that Q2 seems to be a better approximation of P or closer to P because the mode seems to be matching, as well as the height near the mode seems to be matching, the overall distribution of samples seems to be matching, the shape seems to be matching much more closer compared to Q1, right? But this we just looked at it visually. We can also do this via the KL divergence calculations. So firstly, I will be using the inbuilt functions in Torch, the distributions, or equivalently you could have used in TensorFlow. I calculate the distance between the KL divergence between Q and P. So this is the first Q is parameterized by 0, 2, the second one is Q2. And as you can notice, the KL divergence between the Q2 which is parameterized by mean mu, mu equal to 1 and sigma 3, is much lower compared to the normal distribution parameterized by mean 0 and scale 2. So, as expected, as we have seen visually, Q2 seems to be closer fit to P, or the divergence between Q2 and P is lower than the divergence between Q1 and P. Okay, so this was an easy problem. Let's consider the problem. Can you tell me the optimum mu and sigma which would minimize the KL divergence between a Q and a P, with the Q is parameterized as normal distribution with mu and sigma? How will we go about that? Same as the one in
P.
So here we know that P is given as a normal distribution, but let's assume that P is not a normal distribution, it's some other distribution whose form we don't know, right? So P is an unknown distribution to us. It's some distribution whose prob, log prob, all those methods we have, but we have another distribution Q which we want to get as close as possible to P, and as our definition of as close as possible would be given as the KL divergence, minimize the KL divergence between a Q and a P and the P. How do you think we'll go about that? Yes. We can use the KL divergence as a loss function, right? That is all we need to do, not a very sophisticated problem. So firstly, if we didn't want to solve it as an optimization problem, but rather as a grid search problem. So you can always solve simple optimization problems as grid search problems. We have P, which is normal 1, 4, and then I've created 4 different Qs, 0, 1, 0, 2, 1, 1, 1, 2. If you were to just look at these, you would probably think that the Q parameterized as normal distribution with mean 1 and scale 4 is showing the lowest KL divergence, lowest KL divergence given Q given P. Right? So we would have chosen that if these were the values that we would have chosen. So this is the simple optimization that I am showing. Now this is not a neural network, so you'll have to create tensor variables with required grad equal to true. In neural network libraries, whenever you're using nn.module, etc., these things are automatically handled for you. So I create these 2 variables, torch tensors and requires grad equal to true, and I pass them in my list of parameters. I give a learning rate equal to 0.05. Why do you think I'm using this? Scale soft plus equal to torch.functional.f.soft plus of scale. So gradient descent like methods, they typically like to work in what space? Constrained, unconstrained? Unconstrained. But a scale is a constrained factor, right? We can't make it less than 0. So this soft plus function would be similar to exponentiation function, something like that, which will make it non-negative. You can look at the definition also. So it's log of 1 plus e to the power x. So I could have also done just exponentiation of scale, but I've here chosen this.
What is the constraint here?
Scale we are using, so we have a normal distribution. Normal distribution is parameterized by mean and the location of the location and the scale has to be greater than equal to 0, greater than 0. So therefore we have to create a non-negative quantity here. And then I'm just saying that this is my 2 learned distribution, which is parameterized by location and soft plus, and I define my loss as a KL divergence between Q and P, and then I just need to call the gradient update rule. So, and over the iterations, you'll see that the scale stabilizes to 4 and the location stabilizes to 1, which was the true set of parameters that we had. Yes.
So here if we use log of scale, then that will also satisfy.
Yeah. We could have also used log of scale here, and while defining the normal distribution, we could have done exponentiation of that. Soft plus exponentiation, there are various such transforms available. And the animations are also very cool if you notice. So here the Q is being improved, the we are minimizing the KL divergence. You can see the objective is being reduced over the iterations, and Q is also trying to now take the shape of P, and it will gradually just superimpose. Okay, this was an easy problem. We look at variants of this problem. First, to find out the KL divergence for two distributions from different families. So by family of distributions, I mean like normal distribution is one family of distribution, beta could be another family of distributions. Between normal and normal, it's a simple problem, and we can already define it. But between two different distributions, we cannot very trivially do that, right? But before that, let's work out something in your notebooks. I want you to find out the KL divergence between two Gaussian distributions. This will be a good exercise in ensuring that you remember the rules of expectations, etc. So first, why don't you note this slide, which is writing the formula. I would suggest you don't directly go with and open this integral. First, you write in this term in the form of expectation, simplify it, and then try and compute the expectation over the simplified quantities. Can I move to the next slide? Has everyone noted this formula? Okay, this is the problem statement. And you have to find Q given P, so exactly the same formulation as written previously. And you're more than welcome to discuss with your neighbors. Okay, I've written the first three steps for you. That's the answer. Okay.
Log sigma p equals sigma q plus sigma q square plus mu q minus mu p whole square equals to sigma p square minus half.
Okay. So answer is more or less sounds correct, but some terms can be simplified. A minus b the whole square. Try and write. Okay, in the interest of time, I'll go over the solution and I'll maybe pause again after a couple of minutes to see if you can finish out from here. We start with the definition of Kerr divergence, which is just writing in terms of the expectation with respect to q theta, log of q theta by p theta. I just substitute the value of q theta as the PDF, which is 1 over root 2 pi sigma q square and e to the power minus theta minus mu q over 2 sigma square. So we then expand these terms and I write log of a into b as log of a plus log of b, and log over a divided by b as log a minus log of a. So this is in terms of the power, so I'm just doing the manipulation of the power. So this was a minus here, minus becomes a plus. And then log of exponentiation of something is, you just write that something quantity. And this term we'll then subtract out, we'll just cancel out, sorry. And I'm expanding this out. So you get theta square minus 2 theta mu q plus mu q square whole square, plus similarly I've expanded out the square here. And then I've just written down all of these terms. So term 1, 2, 3, 4, 5, 6, 7 terms, and I'll calculate the expectations over these. So firstly, we can just simplify this term, and we can write this as log of sigma p over sigma q. Can everyone see this? Log of sigma p over sigma q, the first term, and then using the linearity of expectation. So this is expectation over q of theta of this entire term. Now some of the terms are independent of theta, right? Some of the terms are linear in theta and some of the terms are quadratic in theta. So we just need to know the expectations of terms independent of theta, linear in theta and quadratic in theta. So we know that if theta is distributed as q theta, which is normal with mu q and sigma q square, then the expected value of theta is mu theta, and the expected value of theta square is sigma square plus mu square. Right? All of them are subindexed with q because this theta is distributed as q. Right? So these are the things you'll need. We will now substitute. So here, instead of expected value of minus theta square over 2 sigma q square minus 1 over 2 sigma square, q can be kept constant, and then you are trying to put this substitute the value of theta, expected value of theta square, which we can plug it from here, sigma q square plus mu q square. Similarly, you have a linear in theta, you just substitute this as mu q. You have independent of theta, you don't need to put anything. The expected value of this is the same value itself. Again, you put mu q square plus sigma q square. Again, you put mu q, and this term is kept independent. So once you do a bit of simplification of each of these terms, you will get something like this: half common logarithmic of sigma p square over sigma q square minus half plus mu p minus mu q whole square over sigma p square plus sigma q square by sigma p square. All of the terms here are in the denominator have sigma p square. So we can also write this as minus log sigma p square over sigma q square, so that it's easier to remember. Right? So it's a bit of calculation. Now if you go into torch.distributions, yes, the log term is incorrect. No, I have kept the half. Yes. So if we look at KL divergence and we go to the source, so this is giving the distributions, the KL divergence between pairs, between families of distributions. So here also you can see they are using soft plus. So here we have to search for normal, comma normal. Right, this is the way they have defined. This is P and Q, we are doing Q and P, so everything would be reversed. They calculate a variance ratio, P scale, Q scale power 2. So we have term P square, P dot scale, Q dot scale. So it's this term, sigma P and sigma Q. You find out these terms, you square them, and then you have P dot log minus Q dot log. So you have mu P minus mu Q, and then you square that, and then you have half into variance ratio plus T1 minus 1. So variance ratio is P over Q square. So we'll have reverse because we are doing Q and P. So this term plus, so we have this minus 1 also common, and T1 was this term, right, and variance ratio dot log and logarithmic of this, right. So we can verify that this is indeed what is being used in the code. Any questions on this? It's a bit of a DDS calculation, but but this is how different libraries will have implemented in the closed form. Okay, coming back. So we've figured out how to find the KL divergence for two distributions from the same family. We can do exactly what we did a few minutes back. We can carry out these expectations, we can find out, solve them analytically, and we'll get some expressions, and then we can code these expressions up. But if the two distributions are from different families, so in this case I am creating a mixture of Gaussians, and this is how the mixture of Gaussians looks like. You can very clearly see that there are two Gaussians which I've added up, and I have now shown with this mixture of Gaussian, I have showed two different Q distributions, Gaussians. Which of them do you think is a better fit for the mixture of Gaussian, Q1 or Q2? Q1 seems better. So the only way we can ascertain this is to compute the KL divergence between Q1 and the mixture of Gaussian and Q2 and the mixture of Gaussians. And whichever is the lower number, we will say that that is a better fit. And let's try and do that in code. So dis.KL divergence between Q1 and PS, right? This PS is the mixture of Gaussians, and we will get this exception, KL divergence not implemented between normal and mixture same family, right? So we cannot compute the KL divergence analytically between normal distribution and a mixture of Gaussians. So what do we do then?
Use some sampling method.
Okay, what kind of a sampling method can we use?
MCMC.
MCMC, we don't need MCMC here. So remember that, let's go back to the formula. Yes.
So eventually we need to find out the expectation of logarithm of q of theta by p of theta.
Where theta is?
Theta is the parameter for the distribution.
Right, no, where theta is distributed as per Q distribution. Right, so we want to compute this quantity. We cannot compute this in the closed form, therefore we'll have to use some other method and
We can sample and then average.
we can use Monte Carlo sampling, right? So all we're saying is that okay, I've not written the math here. All we're saying here is that we sample from Q distribution, right, to get a set of samples, and then we do Q dot log prob of those samples minus P dot log prob of those samples and take the mean over them. And this is just the standard Monte Carlo sampling. Right? We replace this expectation as 1 over n log of q theta I over p log of q theta I over p theta I, where theta is distributed as q of theta. And that's exactly what we are doing in this piece of code. We get a set of samples and we're putting q dot log prob of sample set minus p dot log prob of sample set. So now we can firstly, whenever we write such code, we should use it on distributions for which we know the closed form solution. So here q1 and q2 are both univariate normal distributions, and we use a sampling method and we get the K divergence between them as 1.0288, which is the true analytical expression. And if we were to instead use Monte Carlo sampling, we get 1.0309. Now this will have the usual problems with Monte Carlo sampling, that the variance will be reducing not very quickly with respect to the number of samples. You can also play around with the number of samples and see the different answers that we'll get. So 1.2, 1.0, right? So as we'll increase the number of samples, we'll see that we'll start getting better estimates. Right? So we can keep doing this. Now using this method, we can compute the KL divergence between Q1 and P of S, where P of S is a mixture of Gaussians, and Q2 and P of S again, where P of S is a mixture of Gaussians. And now from this expression, it seems that Q1 is closer to P of S as per KL divergence as compared to Q2. And we'll go back and look at the graph. So the KL divergence between Q1 and P is lesser than the KL divergence between Q2 and P, which we saw visually, but we cannot compute that analytically. So therefore, we use Monte Carlo sampling to find out this value. Right? So this was the case when we wanted to find out the KL divergence between two distributions from different families. But let's get back to the earlier problem. We want to optimize the parameters of Q, which is mu and sigma, such that the KL divergence between Q and the target distribution P is minimized. Right? I showed that previously how we could do that, but there we had the analytical expression available. Right? In this example, we looked at location and scale, and all we had to do is to create a distribution, dis dot normal with location and scale, or the exponential or the non-negative version of the scale, and then analytically find out the KL divergence between the between the new distribution and the target distribution, right? But can we do the same thing here, where we, instead of using the analytical expression, we are using Monte Carlo sampling? Yes? No? How many think we can? Okay. So let me first show you what is happening. Right, so this is the original formulation. We have two kinds of nodes, deterministic nodes and stochastic nodes. Stochastic nodes are wherever we have some notion of randomness. And this is the loss function that I had written a few minutes back. We have distribution.normal, location and scale, or the softmax of scale, whatever. So the exponential of scale. I create a sample set, which is from Q distribution. I create n samples, and then I find out the mean over Q.log prob of sample minus P.log prob of sample. If you look at the computational graph, we start with location and scale. These are quantities which we'll, let's assume them to be deterministic. We'll create a Q distribution. We generate samples from them, and if you notice, the loss is computed over the samples, right? So our goal is optimize the location and scale such that the loss is minimized. So if we have to go back and do back prob, we have to go through this stochastic node, right, which causes problems. We cannot go back via stochastic node, so it's also very implementation specific. In fact, if you wrote this code and you use torch, this will work. So just few minutes before the class, I was attempting to show that this code won't work, but this will work in torch just because of the way as they've internally implemented the solution to the problem which I'm showing. Right? So does everyone broadly understand the problem here? The computational graph, you can think of it as getting disconnected, and the gradients don't have a path to flow from the loss to the parameters we want to optimize, location and scale. Okay, how do we solve this problem? The answer is known as reparameterization trick. So now you have to think, what does reparameterization mean? If you remember the previous lecture on Bayesian optimization, we did indeed use the exact same term, reparameterization trick. Okay, excellent. So the hint is that we have to use the standard normal somehow, and that is what is the reparameterization trick. By the way, how many of you have heard of variational autoencoders? Okay, so anyone who's used variational autoencoders have heard of this. They use the same trick there, which is the reparameterization trick. I can the paper is called Auto-encoding Variational Base from 2013, 2014 or so. The reparameterization trick. So it's exactly the same thing which we'll use today. So this is a loss function which will not allow us to back propagate. In contrast, let's look at a slight variation. I create samples from the standard normal, which is mean 0, scale 1. I have my location and scale. I do scale into samples. So I create standard normal, which is this dot normal location and scale 1. I sample from that n samples, and then I modify my sample set to location plus scale into sample set, right, which is the standard reparameterization trick. You multiply scale to the samples at the location, then you get a quantity, let's call it that z, which is then fed into the loss. So because of this new manipulation, the we are able to back propagate to both the location and scale, the gradient flow back, and thus we can learn. If we look at this code, this is the same like this above screenshot is from this code only. I have shown the original function and I have shown the reparameterized version, and I am using 5000 samples, and I am saying that my location and scale are like this. I have again a scale soft plus. I've here hard coded things like the PS, which is a mixture of Gaussians, and so now the parameters that we have learned after the optimization, right? So does this Q seem like a fairly good fit to P? The thing which I was just saying earlier, so I'm currently using the loss function, which is the reparameterized loss function, but instead if I use the original loss, we would have expected the code to fail, right? We should not have been able to compute the losses. So everything else remains the same. I am just changing the loss function. Okay, now it seems to have not worked actually. Okay. The values are indeed changing, but they are only very minor changes. Okay, I will leave this specific problem as the Schrodinger's cat. I don't know whether internally it is using reparameterization trick or not. I previously assumed it is, but now I'm not sure.
Like even if after reparameterization we are able to get the computational graph, isn't it very computationally expensive because every time for all those big set of samples in gradient descent, for every iteration we are again doing a Monte Carlo sampling.
So it is not very cheap, but you can look at how quick it is happening. Right? So generating of samples is very easy. So internally, in fact, if you look at any library's implementation for sampling from normal distribution from mu and sigma, this is what they'll internally do. But now you have specifically given this location and scale outside, and you've made them learnable. This is the only difference. Typically, you would not have location and scale as learnable. So it works fairly quick. Practice. Can't we use the samples? Okay, so do you want to use the same set of samples again and again? You are introducing some notion of bias that way. If you have enough samples, yes. We can take a very large number of samples and then you can do it over the same set of samples, right? So there are variations to this, as you're mentioning. So I think that particular approach, if I'm not mistaken, it's called deterministic. I don't know whether it's the same term or not. I can look this up and let you know for the next, in the next class. So it says that instead of working with a new draw z at each step of the optimization, we can use a single set of draws at the start and keep them fixed during the optimization. So this is perhaps what you're pointing out to. So this is known as deterministic variational inference. You draw the samples once, and in a JAX-like network, it means that you have you fix the random seed, the random number generator, and you draw a set of samples, and then you just keep reusing those. Okay, other questions on this? I will move from the original loss to the loss. And the objective is getting optimized now. And you can view with respect to the animation also. I'm just showing it for a few iterations. I'm not showing it for all the iterations, but you can very clearly see that it's moving towards the distribution of interest. So I have a topic which would require a bit of concentration. Do you want me to cover it today or the next class? We still have enough time, 19 minutes. Okay. So the problem where we're trying to use variational inference thus far is, let's go back. It's this setting. We are trying to compute the optimal set of parameters for a distribution Q, right, whose scale divergence between Q and P we are minimizing, where P I have written as the posterior, right. So P of theta given D. Do we have access to the posterior? No. How do we compute this term then? So that's the beauty of machine learning and the problems. Like, we start with something and then this doesn't work and this assumption is failing, and now this is the central problem we tried to solve at the beginning, right? And we don't even know what is P of theta given D. If we knew P of theta given D, then is this problem worth solving? Right? If we knew P of theta given D, then just use P of theta given D. But we don't know P of theta given D, so we're trying to now optimize the K divergence between some Q and P, but we cannot do that because P of theta given D is unknown. So what do we then do? Okay. Okay, so let's go over these terms slowly. We are trying to minimize the K divergence between Q of theta and P of theta given D. I have just expanded out, right, K divergence between Q of theta and P of theta given D, where Q is parameterized by some psi, right? Psi is mu and sigma for a normal distribution. So this is the expectation I have written, right? So why don't you do a bit of exercise? That can you write the Bayes rule here, P of theta given D, right? Can you expand that by the Bayes rule in terms of things you know and you don't know? We typically know the prior and the likelihood. We generally don't know the evidence. So why don't you just substitute P of theta given D from what you know in the Bayes rule? Okay, has everyone written? Can you write it like this? The K divergence between Q and the posterior is the expectation of Q theta into P of D divided by the joint logarithmic of that quantity, right? Now we can just expand these terms out, which is equivalent to the expectation of log of Q theta minus expectation of P of theta comma D, which is the joint, plus the expectation of log of P of D given under Q theta, right? What can you think about the last term? What will that evaluate to? Yes, what does it evaluate to? Same, because it has independent of theta, right? So we can then write this as the K divergence between Q of theta and P of theta given D, or K divergence between Q and the posterior, is expectation of log of Q theta minus expectation of log of the joint plus the log of P of D, right? Now let's look at these quantities. As per the definition of K divergence, it's a non-negative quantity, right? You're trying to compute some notion of divergence between two distributions. It is equal to 0 only when the two distributions are exactly the same, right? Otherwise, it's always greater than equal to 0 plus log of P D term, and there is this term which we are calling minus ELBO, right? Any guesses on what this might stand for? It's a very strange term. Okay, good guess. Expected loss between an O. Objectives. Okay. Anyone else? So E stands for evidence, and this term is also known as the evidence, right? Log of P of D is the evidence term or the marginal likelihood term. Evidence, lower bound, right? Why is it the lower bound? So we know that the KL divergence is greater than or equal to 0. We know that we have this quantity, and then log of P of D is lower bounded by this term, right? So let me see if I can. Right. So can we think of this way? Log of P of D is greater than or equal to elbow, right? So the way this is typically shown is, okay, I wanted to show a diagram drawing. Let me see if I can do some. I can figure out from. Okay, I don't know if I'll be able to find the exact drawing which I saw. Okay, indeed, I'm able to find this one. Right, we have the elbow term, right, and our evidence term is log of P of. You can just think of this as log P of D, right? They are using slightly different convention, and the difference between the evidence term and the elbow term is the KL divergence, which we are trying to compute, right? If the KL divergence between these two quantities is 0, which means our Q is exactly the same as the posterior, in that case, our evidence is lower bounded by elbow, right? So the evidence will be always greater than this quantity elbow by the KL divergence quantity. So this was the reason I was a little hesitant in starting this topic. It's a little involved, But essentially what we have seen is that we had the original problem was what? Minimize scale divergence between Q and the posterior, right? Can we think of P of D as some constant, right? So therefore, we wanted to minimize the scale divergence, which is equivalent to minimizing negative elbow, right? So that becomes a new objective. Even though we don't know this quantity P of D, we know everything else in the elbow definition, right? So therefore, minimizing scale divergence is equivalent to minimizing the negative elbow or maximizing the elbow. Is everyone clear, or do you want me to go over this again? Yes.
Like we don't know the value of the constant, so while minimizing, how can we constrain it that the overall thing is greater than 0?
How can we? So we know for sure that scale divergence between any pairs of distribution has to be greater than or equal to 0. So we know that it's greater than or equal to 0 as per definition. Now all we are saying is that this is some constant which does not take part in the optimization. Therefore, you consider all the other things which are not a part of that expression.
Like suppose we are using gradient descent like method to minimize that function. So what if the value goes below the constant which is of the evidence?
Okay, so Bhavish's question is that what if the elbow goes below that constant? I don't know whether that will go below the constant or not. So typically when we will be computing this elbow, we would again be having the same issue as previously. We will not have the analytical form, etc., or we can just expand this out, the expectation out. So we will have to do this via the sampling method only. Each time you do sampling, you may be given a new set of samples, and does anyone else have thoughts on this? Scale divergence has to be greater than or equal to 0, and that particular quantity is just a constant.
But anywhere we are not ensuring that because we don't know the constant, we are not ensuring it will be above or below that value. So it can go.
Yeah, I don't know the exact answer to this. The way I might go about testing this out would be to use Monte Carlo sampling to also compute log of P given T, right? Now for every different set of samples, I will also learn a slightly different value of the log of P of T. No, I don't have a crisp answer. We can discuss this again in the next topic, in the next class. But is everyone clear with the derivation? Do you want me to repeat? Right, so the important thing you want to remember at the end is this diagram, that the evidence term is lower bounded by the elbow term and the scale divergence is the gap between them. Our objective was to minimize the scale divergence, which ends up being equivalent to maximizing the elbow or minimizing the negative elbow, right? And P of D is assumed to be some constant. So in the next class, we would want to use the formulations that we studied today for the coin toss problem and then hopefully for linear regression, right? So again for the coin toss problem, we will look at the posterior. We can use the true posterior or we can use the approximate posterior and we'll see. The posterior only up to a constant and we'll see, and then we'll have to use a target distribution Q, which we can parameterize by anything we want. Like in this case, Q could be a normal distribution parameterized by mu and sigma, and we'll then try and minimize the scale divergence between Q and the true posterior. Similarly, we'll have to do this for, we can try and do this for linear regression like problems. And then finally, when we have to scale this to something like neural networks, we'll have to make a lot more assumptions. We'll have to make certain assumptions on the parametric form that you want for Q. Typically, we end up choosing Q as a multivariate normal, where we are only looking at the diagonal terms in the covariance. Right? We don't consider the relationship between all of the